The Boltzmann factor. For an event to occur, sufficient particles must have enough energy to carry out that event. The event could be a change of state, it could be a chemical reaction, or thermionic emission from a metal, ionization, or conduction in semiconductors, or molecules moving past each other in a liquid, allowing it to flow, for example. If the energy needed, epsilon, is around 10 to 30 times the average energy of the particles, kT, K being the Boltzmann constant and T the temperature in Kelvin, then the event will take place at a reasonable rate. The Boltzmann factor tells us the fraction f of particles in a sample that will have this higher energy, giving f equal to e to the minus epsilon over kT. I've copied the Boltzmann factor across here for reference. As we saw on the energy and reactions video, when energy over kT is between about 10 and 30, here I've picked the middle value of 20, events are likely to take place at a reasonable rate. Epsilon here is the energy required for the event to take place. kT gives us the average energy of the particles involved. The Boltzmann factor at this level is given by e to the minus 20, which comes out at 2 times 10 to the minus 9. This means only around 1 in 500 million of the particles will have sufficient energy to carry out the event. This seems to suggest that the event will be extremely unlikely, if only around 1 in 500 million particles can take part. However, if we consider that a litre of water contains around 3.3 times 10 to the 25 molecules, this means about 6.8 times 10 to the 16 of them will have 20 times the average energy. These figures tell us that it is extremely unlikely for any one particle to gain 20 times the average energy, but there are so many particles involved that extremely unlikely events do occur, and to a significant number of particles. If we look at a different case, it would be extremely unlikely, but not impossible, to pick the winner in 10 consecutive horse races. If there were 8 horses in each race, each with as much chance of winning, the chances would be 1/8 to the power 10, or 9 times 10 to the minus 10. This means it would occur only once in every billion, or 10 to the power 9 times. However, if the entire population of the world, around 6.6 billion people, attempted this, it's likely that it would happen to around 6 lucky people. With atoms and molecules, we have unimaginably large numbers, and they're interacting an unimaginable number of times every second, and so the extremely unlikely is a regular occurrence. Here we have a table showing the Boltzmann factor in this right-hand column for the process of vaporizing water molecules. This requires an energy of 6.8 times 10 to the minus 20 joules per molecule. The Boltzmann factor tells us the fraction of particles which will have this level of energy. We're going from a temperature range of 150 Kelvin to 450 Kelvin. Now 150 Kelvin is minus 123 degrees Celsius, and so clearly at this temperature effectively no water molecules will vaporize, whereas 450 Kelvin is 177 degrees Celsius, and there would be rapid vaporization of water molecules at this temperature. You'll see energy over average particle energy, kT, is going from around the magic 10 to 30 range. Below 10, and reactions are effectively instantaneous. Above around 30, and they occur incredibly slowly. The most striking thing here is the rapid change in the Boltzmann factor. In going from 150 to 200 Kelvin, we increase by a factor of around 10,000, from 10 to the minus 15 to 10 to the minus 11. In going from 200 to 250, we increase by a factor of around 100. In going from 250 to 300, it increases by a factor of around 10. Likewise, going from 3 to 350, from 350 to 400, and from 400 to 450. So in any particular sample of water, if we raise the temperature from 150 to 200 Kelvin, we'd get around 10,000 times the number of particles in a position to vaporize. In going from 200 to 250, we'd have around 100 times more particles available, and so on. If we plot a graph of these values, it goes something like this, with temperature on the x-axis and the Boltzmann factor on the y-axis. There's very little change along here, then a massive shoot up at this point. Here's another table and graph, this time for a fixed temperature of 300 Kelvin, but I'm raising the energy from around 4 times 10 to the minus 20 joules up to 12 times 10 to the minus 20 joules. Again, you see energy over kT covers the magical range from around 10 to around 30, and now in going from 4 times 10 to the minus 20 just up to 6 times 10 to the minus 20, there's a massive drop off in the number of particles able to carry out this event.